Hello again, students. Our next topic takes us into the realm of plastics and their remarkable properties. We've all heard of plastics, but did you know there are different types? Today, we're delving into thermosetting plastics, which stand apart from their counterpart, thermoplastic. The key distinction lies in their behavior when heated. While thermoplastics can be melted and reshaped multiple times, thermosetting plastics are set through irreversible chemical processes. This means once they take their shape, they're there to stay. Imagine a moldable substance turning into something permanent. A familiar example is vulcanized rubber, commonly used in tires and various industrial applications. Another instance is polyurethane, found in insulating foams and comfy mattresses. These plastics serve a variety of purposes due to their unique characteristics. Now, let's proceed to explore more captivating concepts. Hello again, students. Today, we're delving into the realm of materials that showcase remarkable flexibility and resilience. We're talking about elastomers. Elastomers are unique substances that demonstrate rubbery or elastic behavior. Imagine a material that can stretch or bend and then magically spring back to its original form once the stretching force is removed. This incredible property is a result of the material's capacity to restore itself, as long as it hasn't been stretched or bent beyond a certain point known as the elastic limit. You might have encountered elastomers before without realizing it, but one well-known example is rubber. So, just like a rubber band, these materials possess the ability to bounce back, maintaining their shape even after deformation. Now, let's explore this fascinating concept further. Hello again, students. Today, we're delving into the intriguing world of polymerization reactions and focusing on a specific example, the formation of polyethylene. So, what exactly is polymerization? Well, it's a process where smaller units called monomers are joined together to create larger chains known as polymers. Our spotlight today is on the transformation of ethene molecules into polyethylene. Imagine a chain reaction where ethene molecules undergo a fascinating change. The double bond in each ethene molecule opens up, and here's where it gets exciting. Two of the electrons that were initially part of this bond come together to create new C-C single bonds with two other ethene molecules. This specific type of polymerization, where monomers are linked through their multiple bonds, is termed addition polymerization. Let's proceed to explore this process further. Hello, student. Welcome back, dear students. Today, we're dissecting the mechanism behind the formation of polyethylene. Picture this. Ethene molecules, which are small and simple, undergo a transformative process. The double bond in each ethene molecule undergoes a remarkable change, it opens up. As a result, two electrons, originally part of the double bond, are now available for sharing. These electrons form new C-C single bonds with other ethene molecules. This cycle repeats itself, leading to the creation of a chain, a polyethylene chain. Think of it like a never-ending dance, where each molecule joins hands with its neighbors, creating a strong and flexible chain. This process, where ethene molecules join together, is known as addition polymerization. Let's move on to our next exciting topic. Welcome back, dear. Hello again, bright minds. Our journey into polymerization continues with a closer look at addition polymerization and its impact. Addition polymerization is a fascinating process where monomers, those building blocks of molecules, are coupled together through their multiple bonds. We've already seen how ethene molecules bond through their double bonds to create polyethylene chains. This process results in sturdy and durable polymer chains that have a variety of practical applications. Think about everyday items like plastic bags, containers, and even certain types of clothing materials. These are all made possible by the versatility of polyethylene. As we delve deeper into the realm of chemical reactions, remember that these transformations pave the way for countless innovations that shape our modern world. Hello again, greetings, inquisitive minds. Let's broaden our perspective by exploring the practical implications of polymerization reactions. We've learned about the fascinating process of addition polymerization, where monomers unite to form polymers with distinct properties. It's important to note that polymerization isn't limited to just one type or product. There's a diverse world of polymerization reactions, each leading to a unique set of products. Consider the variety of plastics, rubbers, and fibers that have revolutionized industries and our daily lives. From soft and flexible materials to rigid and robust structures, polymer chemistry plays a pivotal role. As you can see, the intricate world of chemical reactions drives innovation across various fields. Greetings. Hello again, dear students. Let's move forward in our exploration of chemical reactions and energy by delving into the intriguing world of polymers and monomers. Imagine a chain made up of repeating units. This is what we call a polymer. To create this chain, a large number of monomer molecules, like ethene, come together in a fascinating dance of reactions. Keep in mind that N in our discussion represents the number of monomers involved, which can range from hundreds to even thousands. As these monomers connect, they form a remarkable polymer chain, and each repeating unit within this chain is shown in the equation. Picture this as a beautiful pattern that extends throughout the entire chain. But what about the ends of the chain? They're capped by either carbon-hydrogen bonds or other bonds, ensuring that the end carbons are fully bonded, having 4 bonds each. Now, let's take a closer look at how these polymers are created and understand the structural aspects that make them so fascinating. Hello again. Welcome back, inquisitive minds. Today, we're peeling back the layers of monomers and polymers. Monomers, my dear students, are the building blocks of polymers. Think of them as the individual pieces of a puzzle. These pieces, when joined together in a specific way, create a stunning picture, the polymer chain. We call this process polymerization, and it's a result of carefully orchestrated chemical reactions. These reactions involve the monomers bonding together in a chain, repeating the same unit again and again. This repetition gives rise to the incredible structural diversity we see in polymers around us. Remember, the choice of monomers and the way they bond together determine the properties of the resulting polymer. So, the next time you encounter a plastic object, remember the journey of monomers coming together to form that durable and versatile polymer. Welcome back. Greetings, young scholars. Now that we've grasped the magic of polymerization, let's dive deeper into how polymer structure influences their properties. You see, the arrangement of monomers and the length of the polymer chain directly impact the characteristics of the final product. Imagine a symphony where each note, monomer, contributes to the grand melody, polymer. The length of the chain, which we call molecular weight, plays a significant role in determining properties like strength, flexibility, and more. Manufacturers can even fine-tune these properties to meet specific needs. For instance, flexible plastics for packaging or sturdy materials for construction. Just think about how your water bottle, made from a polymer called PET, perfectly balances durability and flexibility. So, remember, my dear students, polymer chemistry brings us the materials that shape the modern world. Greetings, young. Hello once more, curious minds. Today, we're uncovering the techniques behind polymerization through 2 fascinating approaches. First, let's journey into addition polymerization. Picture this as a string of beads, with each bead representing a monomer unit. Ethene, a simple molecule, showcases this process beautifully. It adds one monomer after another, like stringing beads onto a thread, to form a long and stable polymer chain. On the other hand, condensation polymerization is like a dance where 2 partners come together and release a byproduct as they bond. It's a bit like creating a polymer while also releasing a bit of energy or water. While addition polymerization gives us materials like polyethylene, condensation polymerization gifts us the likes of nylon and polyester. Each method offers unique advantages and results in polymers with distinct properties. So, my young chemists, as you encounter different materials in your daily life, remember the intricate chemistry that makes them what they are. Hello once more. Hello, dear students. Today, we're embarking on an exciting journey into the realm of polymers and their remarkable properties. You see, not all polymers are the same. They come in a captivating array of physical and chemical characteristics, thanks to their distinct chemical compositions. Our focus now shifts to a table, Table 12.6, which presents a collection of additional polymers formed through a process known as addition polymerization. This process contributes to the creation of various polymers with unique attributes. As we delve into this, we'll explore the diverse physical and chemical properties that these polymers exhibit. So, get ready to uncover the intriguing world of polymers. Hello, dear Welcome back, students. Now, let's dive into the specifics of Table 12.6, where we encounter a collection of common polymers formed through addition polymerization. This table acts as a treasure trove of information, showcasing a selection of polymers that have been synthesized with varying chemical compositions. We'll be highlighting some key polymers from this table, and discussing their unique characteristics and uses. It's truly remarkable how the combination of different building blocks can lead to such an array of materials with distinct properties. This knowledge is invaluable, especially when it comes to industries that rely on tailored materials for specific applications. Welcome back, students. Greetings, young minds. Today, we're not just scratching the surface, we're delving deep into the heart of polymer properties. There's an intricate relationship between the chemical structure of polymers and the properties they exhibit. We'll be uncovering this link, dissecting how different arrangements of atoms within a polymer chain contribute to its physical and chemical traits. Brace yourselves for some intriguing examples of polymers that possess exceptional qualities due to their unique structures. As we journey through this exploration, remember that a polymer's architecture holds the key to its incredible diversity of properties. Greetings. Hello again, eager learners. Now, let's turn our attention to the captivating world of polymer structures. Polymers aren't one-size-fits-all. They come in various forms, including linear, branched, and cross-link structures. This diversity arises from the way polymer chains are linked and arranged. We'll explore the effects of branching, cross-linking, and molecular weight on the properties of polymers. You'll be amazed at how the arrangement of these tiny building blocks can lead to such dramatic differences in functionality. So, keep your curiosity alive as we uncover the secrets of polymer architecture. Hello again. Good day, students. Today's topic takes us into the world of polymers and copolymers. Let's begin by understanding what copolymers are. When polymers are formed from two different types of monomers, they are referred to as copolymers. One intriguing example of this is the formation of nylons. Nylons are created by combining specific monomers, namely diamines and diacids. A diamine is a molecule with the NLT phoneme alphabet equals IPA pH equals Na2 greater than not NH2 group at each end, while a diacid has the NLT phoneme alphabet equals IPA pH equals Na2 greater than not Cu group at each end. These two types of monomers come together to create remarkable polymers known as nylons. For instance, let's delve into the copolymer nylon 6,6. In this case, a diamine with 6 carbon atoms and amino groups on both ends reacts with adipic acid, which also has 6 carbon atoms. This reaction involves condensation at both ends of the diamine and the acid, resulting in the formation of N0C bonds and the release of water molecules. This process of combining monomers and forming copolymers is truly fascinating. Now, let's move on to explore more about the chemistry behind this process. Good day, students. Welcome back, students. Today, we're delving deeper into the synthesis of nylon 6,6, an exemplary copolymer. To create nylon 6,6, we combine a diamine with 6 carbon atoms and amino groups on each end, along with adipic acid, which also consists of 6 carbon atoms. The magic happens through a condensation reaction occurring on both ends of these monomers. As a result of this reaction, water molecules are released, and the molecules are linked together by NC bonds. The formation of these bonds is what gives rise to the incredible strength and durability of nylon. It's intriguing to witness how the structure of the monomers determines the properties of the resulting copolymer. Let's move ahead and explore more about the practical applications and significance of copolymers in our world. Welcome back, students. Hello again, students. Now that we've grasped the concept of copolymers and explored the synthesis of nylon 6,6, let's take a broader view. Copolymers find their way into many aspects of our lives. They are incredibly versatile and are used in diverse industries. From packaging materials to medical devices, Copolymers offer a range of customizable properties that suit different applications. This versatility is due to the fact that by selecting specific monomers and controlling their ratios, we can tailor the properties of copolymers to meet specific needs. This plays a crucial role in materials science, where scientists and engineers work to design materials with desired characteristics. So, next time you use a product made from plastic or encounter a medical device, remember that copolymers have played a significant role in making those advancements possible. Let's continue our journey into the world of polymers and their applications. Hello again, students. Welcome back, curious minds. As we're diving deep into the world of copolymers, it's essential to understand the chemistry that underpins the formation process. The key reaction involved is called a condensation reaction. This reaction occurs between the functional groups at the ends of the diamine and the diacid monomers. During the condensation reaction, a water molecule is released, and this loss of water allows the molecules to join together. The most crucial outcome of this reaction is the creation of covalent bonds between the monomers. These bonds define the polymer structure and contribute significantly to its properties. The nature and arrangement of these bonds influence characteristics like strength, flexibility, and even resistance to heat and chemicals. It's fascinating how a simple reaction can lead to such intricate and impactful outcomes. Let's continue our exploration of the world of polymers and their marvelous chemistry. Welcome back. Hello once again, inquisitive learners. Our journey through copolymers brings us to the realm of applications and innovations. Copolymers play a vital role in creating advanced materials that push the boundaries of technology. One exciting area is the development of specialized coatings and films that enhance the properties of surfaces. Moreover, copolymers are making remarkable contributions to biomedicine. They're being used in drug delivery systems, where the controlled release of medications can have a transformative impact on patient care. As we speak, scientists and researchers are delving even deeper into the world of copolymers, exploring novel combinations and applications. The future holds exciting possibilities, from new materials to enhanced medical treatments. As we conclude today's lesson, remember that copolymers are a testament to the incredible synergy between chemistry, engineering, and innovation. Keep your curiosity alive as you continue to explore the wonders of the scientific world. Until next time. Hello once again. Welcome back, students. Today, we're delving into the fascinating world of polymers and their unique characteristics. Polymers, whether synthetic or natural, are made up of collections of macromolecules, which are large molecules with varying molecular weights. These molecular weights can be spread out over a wide range or grouped closely around an average value, depending on how the polymers are formed. This distribution in molecular weights is a key factor that contributes to the amorphous, or non-crystalline, nature of polymers. Unlike materials with well-defined crystalline phases and sharp melting points, polymers exhibit softening over a range of temperatures. This gradual transition is due to the diverse molecular weights within the polymer structure. Now, let's explore further examples and dive into the intriguing properties of these materials. Welcome back, students. Greetings, students. Today's topic, the amorphous nature of polymers, is truly captivating. Unlike substances with a clearly defined crystalline structure, polymers lack a well-defined crystalline phase. Instead, they undergo a gradual softening process over a range of temperatures. This unique behavior can be attributed to the distribution of molecular weights within the polymer. Think of it this way. Imagine a puzzle where the pieces come in various sizes. These puzzle pieces represent the macromolecules with different molecular weights in our polymers. Their arrangement, much like the puzzle, creates amorphous regions, contributing to the softening behavior we observe. As we continue our exploration, keep in mind how molecular weight distribution shapes the remarkable properties of polymers. Greetings. Hello, dear students. Let's take a closer look at the intriguing phenomenon of temperature-dependent softening in polymers. As we heat polymers, they don't melt abruptly like crystalline materials. Instead, they undergo a transition over a range of temperatures. Imagine a dance floor where the molecules are the dancers. As we add energy in the form of heat, These molecules start moving more energetically, just like dancers grooving to lively music. This increased molecular motion leads to the gradual softening of the polymer. It's important to note that polymers lack a specific melting point, due to their molecular weight distribution. This unique behavior finds applications in various industries, where the gradual transition of polymer properties is beneficial. Now, let's journey deeper into the captivating world of polymer science. Hello, dear Good day, students. Our exploration of polymers brings us to the intriguing effects of molecular weight distribution on polymer properties. The way macromolecules are distributed in terms of weight has a profound impact on the overall characteristics of the polymer. Think of it as crafting a recipe with varying ingredients to achieve different flavors. Similarly, altering the distribution of molecular weights allows us to fine-tune attributes like strength, flexibility, and more. This tailor-made approach is essential for creating polymers that suit specific applications. It's a delicate balancing act, much like an artist mixing colors to achieve the perfect hue. So, as we proceed, remember that the unique dance of molecular weights shapes the incredible versatility of polymers. Good day, student. Hello, class. Today, we're delving into the fascinating world of polymers and their unique structures. Polymers, as you may know, are long chains of repeating molecular units. In some cases, these chains may exhibit short-range order, where they align in specific patterns. Figure 12.40 beautifully illustrates how chains can organize in regular arrays. The extent of this order is measured by something called crystallinity. When a polymer has a higher degree of crystallinity, it means that more of its chains are lined up in an ordered fashion. Now, let's talk about a fantastic process that can enhance crystallinity: mechanical stretching or pulling. Imagine a molten polymer being drawn through small holes, which aligns the chains and boosts crystallinity. Why does this matter, you ask? Well, it's because in the ordered crystalline regions, the intermolecular forces between chains are strong. This results in a denser, harder, less soluble, and more heat-resistant polymer. Just take a look at Table 12.7, where you'll see how the properties of polyethylene change as crystallinity increases. So, we've taken our first step into the world of polymer structures and their impact on properties. Let's continue our journey. Hello, class. Great to have you back, students. Now, let's explore how polymerization, the process of creating polymers, contributes to the variation in molecular weights. During polymerization, a mixture of macromolecules with different numbers of monomer molecules, N, is formed, leading to varying molecular weights. This variety in molecular weights plays a pivotal role in determining the crystallinity of the resulting polyethylene. Keep in mind that as molecular weight changes, so does the arrangement and structure of the polymer. Great to have you back. Null. Bravo, students. Now, let's shift our focus to high-density polyethylene, or HDPE. This variant of polyethylene serves a different purpose and is commonly employed in the creation of bottles, drums, and pipes. HDPE boasts an average molecular weight of around 106 U and a density of 0.94 grams per cc or even higher. One remarkable distinction between HDPE and LDPE lies in their side chains. HDPE features fewer side chains compared to LDPE, leading to a higher degree of crystallinity within the material. This enhanced crystallinity contributes to the strength and durability that HDPE offers. Bravo, student. Hello, eager minds. Let's wrap up our exploration of polyethylene and its crystallinity by understanding how crystallinity affects the properties of polymers. The level of crystallinity directly influences the characteristics of the polymer material. In general, higher crystallinity is associated with greater strength and stiffness, which is ideal for products like pipes and bottles. Conversely, lower crystallinity can result in properties such as flexibility and transparency, making it suitable for films and sheets. The incredible part is that scientists and engineers can tailor the crystallinity to match the desired properties for specific applications. Isn't that fascinating? Hello, eager minds. Well done, students. We've journeyed through the intricate relationship between molecular weight, crystallinity, and the properties of polyethylene. Remember, the next time you encounter a plastic product, you'll have a deeper appreciation for the science behind its creation. From the branching of LDPE to the crystallinity of HDPE, these factors shape the items we interact with daily. As we conclude today's lesson, take a moment to reflect on how even the tiniest variations in molecular structure can have a significant impact on the materials we use in our lives. Keep your curiosity burning, and until next time. Well done, students. Hello again, dear students. In our exciting journey through the realm of chemistry, we now venture into the world of polymers and their fascinating properties. Today, we're going to explore how polymers can be transformed to become stiffer and more rigid. The key to this transformation lies in a process called cross-linking. Cross-linking involves creating chemical bonds between polymer chains. This process can significantly enhance the stiffness of the polymer. Imagine it as if we're connecting these chains, making the entire structure more robust. The more cross-links we introduce, the greater the rigidity of the polymer becomes. This enhancement is particularly prominent in thermosetting plastics. Unlike thermoplastic materials, which consist of independent polymer chains, thermosetting plastics undergo cross-linking when heated. These cross-links grant them the ability to maintain their shapes even under stress. Now, let's delve deeper into the mechanics of cross-linking and its impact on polymer properties. Hello again, dear. Greetings, curious learners. As we proceed through our educational adventure, it's essential to understand how cross-link density influences polymer stiffness. Picture this. The more cross-links we create between polymer chains, the denser the cross-link network becomes. This cross-link density is directly tied to the stiffness of the polymer. The greater the cross-link density, the more rigid and inflexible the polymer structure becomes. This phenomenon is like reinforcing a structure with additional support beams. More beams mean greater stability. Imagine a polymer with just a few cross-links. It would be relatively pliable. On the other hand, a polymer with a high cross-link density would exhibit impressive stiffness and resistance to bending or stretching. This correlation is crucial in designing materials for various applications. Now, let's journey further into the world of polymer mechanics and explore the implications of different cross-link densities. Greetings. Hello once again, eager minds. Today, we're unwrapping the mystery behind thermosetting plastics and their remarkable ability to retain their shapes. First, let's refresh our memories. Thermoplastic materials consist of independent polymer chains that can be melted and reshaped. On the other hand, thermosetting plastics take a different approach. When these materials are heated, they undergo a transformative process known as cross-linking. The introduction of cross-links transforms the thermosetting polymer from a malleable substance into a material with exceptional shape retention. Imagine a polymer that, once molded, holds its form no matter what. This phenomenon is achieved through the cross-links, which lock the polymer chains in place, preventing any significant changes in shape. It's like creating a permanent structure that maintains its integrity under various conditions. With this knowledge, we're better equipped to understand the diverse world of polymers and their applications. Stay curious, and let's continue our exploration. Hello once again. Welcome back, everyone. Today, we're delving into another intriguing concept: cross-linking and the fascinating process of vulcanization. Get ready to learn about a remarkable discovery made by Charles Goodyear back in 1839. We'll be exploring how this discovery revolutionized the properties of natural rubber. As you might know, natural rubber comes from the liquid resin extracted from the inner bark of the Hevea brasiliensis tree. It's composed of a polymer called isoprene, chemically represented as C5A. But what makes this polymer special is its structure. Due to limited rotation around the carbon-carbon double bonds in its backbone, the arrangement of groups attached to the carbons remains rigid. This rigidity plays a significant role in the process of cross-linking. So, buckle up as we uncover the mysteries behind this process and its impact on natural rubber. Welcome back, everyone. Hello, students. Today's exploration continues with cross-linking and its remarkable significance. Let's take a moment to understand what cross-linking actually is. It involves forming bonds between polymer chains, creating a network structure. Now, why is this so important? Well, the effects of cross-linking on material properties are truly astonishing. When we cross-link natural rubber, we're in for a treat. The resulting material gains enhanced strength, elasticity, and durability. Imagine how valuable this can be in various industries where these properties are essential. From automobile tires to industrial machinery, the impact of cross-linking can be seen everywhere. So, let's dive deeper into the transformation of natural rubber through the process of vulcanization. Hello, student. Hello again, eager learners. The magic of vulcanization doesn't stop at cross-links. The properties of rubber undergo a remarkable transformation. Think of it as a makeover for rubber. Post-vulcanization, rubber becomes more resistant to wear, tear, and deformation. This means the material can handle stress and strain without breaking a sweat. Now, let's discuss the real-world applications of vulcanized rubber. From the tires on your bicycles and cars to various industrial products. Vulcanization has made these items exceptionally durable and reliable. It's incredible how a simple chemical process can enhance the way we interact with the world around us. So, let's continue our journey into the realm of chemical transformations. Hello again. Welcome to the final stretch of our discussion, dear students. Let's take a moment to acknowledge the visionary behind the discovery we've been exploring. Charles Goodyear's name is synonymous with innovation and transformation. His discovery of vulcanization revolutionized the rubber industry, opening doors to modern manufacturing and technology. Thanks to his pioneering work, we now have access to materials that shape our world in ways we couldn't have imagined. As we conclude our journey through cross-linking and vulcanization, remember that scientific breakthroughs like these ripple through history, leaving a lasting impact on how we live and interact with the materials around us. Welcome back, students. In this lesson, we're delving into a process called vulcanization that plays a crucial role in modifying the properties of rubber. Let's start with the basics. Natural rubber is formed from isoprene monomers, which come together to create a polymeric structure. Now, what happens when we want to enhance the rubber's properties? This is where vulcanization comes in. By introducing sulfur into the rubber, we initiate a fascinating transformation. Carbon-sulfur bonds are formed, creating a network of interconnected chains. But that's not all. Sulfur also facilitates the creation of sulfur-sulfur links between these chains. This intricate process results in a stronger and more durable rubber material. Imagine the applications and benefits this can have. Now, as we move forward, let's explore more captivating examples that showcase the incredible power of chemical reactions. Welcome back, students. Hello again, students. Today, we're building upon our knowledge of chemical reactions and their transformative abilities. Our focus remains on vulcanization and its remarkable impact on rubber. As we discussed earlier, the introduction of sulfur into rubber leads to the formation of carbon-sulfur bonds. Additionally, sulfur plays a dual role in creating sulfur-sulfur links between chains. This intricate bonding results in rubber that's not only stronger but also more durable, making it incredibly useful for various applications. Think about tires, footwear, and various industrial uses. Vulcanization transforms rubber into a material that can withstand a range of conditions. But remember, this enhancement is just one example of how chemical reactions can modify materials and open up new possibilities. So, let's continue our exploration into the fascinating world of reactions and their impact. Hello again, Greetings, curious minds. Today's journey continues as we extend our understanding of how chemical reactions led to remarkable transformations. We've already seen how vulcanization changes the properties of rubber. Now, let's widen our perspective. Chemical reactions, as we know, hold the power to modify the properties of substances, and this is evident in a multitude of everyday items. Rubber is just the tip of the iceberg. From plastics that revolutionize packaging and manufacturing to specialized coatings that protect against corrosion, chemical reactions are at the heart of these transformations. As we progress, we'll delve into more examples that shed light on the incredible versatility of reactions. So, keep your curiosity ignited as we venture further into the realm of chemical wonders. Greetings, Null. Null. Welcome back, students. In our quest to understand the fascinating world of chemical structures, let's delve into the specifics of natural rubber molecules. Picture this. The chain extensions in natural rubber molecules have a unique arrangement. They're found on the same side of the double bond, resulting in a distinctive configuration. To visualize this, take a look at figure 12.42 on the screen. This illustration provides us with a glimpse into the structural intricacies of natural rubber. Isn't it amazing how the arrangement of atoms can lead to such diverse properties and applications? Let's continue our exploration. Welcome back, students. Alright, students, before we dive into the discovery, let's familiarize ourselves with natural rubber. While it's a polymer, it has certain shortcomings that limit its applications due to its softness and chemical reactivity. But, as we'll soon see, science has a way of transforming limitations into opportunities. Alright, students. Now, let's meet Charles Goodyear, a figure who stumbled upon a revolutionary concept. He accidentally discovered that the addition of sulfur and subsequent heating could significantly alter rubber's properties. This accidental breakthrough set the stage for a profound transformation. Now, here's where the chemistry gets interesting. The process involves sulfur cross-linking, which changes rubber into a thermo-set-ting polymer. During this process, the polymer chains form cross-links through reaccessions at specific double bonds. Quote, "This transformation is crucial for the rubber's new-found properties." Quote, "Here's where the chemistry." As the crosslinks are formed, rubber's behavior changes dramatically. When stretched, these crosslinks play a key role in preventing the chains from slipping, leading to enhanced elasticity and durability. The result is a rubber that's not only flexible but also highly resilient. As the crosslinks. Now, what did Goodyear name this transformative process? He chose to call it vulcanization, drawing inspiration from the Roman god of fire, Vulcan. The name reflects the significant role that heating played in this process. Vulcanization turned out to be a game-changer in material science, as we'll continue to explore. Now, as we wrap up our exploration, let's consider the impact of vulcanized rubber on the world around us. The advantages of this transformed material led to a diverse range of applications. It became a cornerstone of various industries, making a mark on our daily lives that we might not even realize. As we wrap. And there you have it, students. The journey from natural rubber's limitations to the creation of vulcanized rubber is a testament to the power of scientific exploration and accidental discoveries. This story reminds us that breakthroughs can happen when we least expect them, leading to innovations that shape our world. As we continue our studies, keep in mind that curiosity and observation can pave the way for remarkable achievements. Until next time. And there you have it. Welcome back, dear students. Today, we're delving into the captivating realm of polymers and their intriguing electrical properties. As we've learned, most polymers consist of sp3 hybridized carbon atoms that lack those wandering p electrons. Consequently, they tend to be electrical insulators, and their colorlessness is attributed to a significant band gap. However, prepare to be amazed, because if the polymer's backbone features resonance, something remarkable happens. The electrons within the polymer can now venture on a journey of delocalization over vast distances. This phenomenon transforms the polymer, enabling it to exhibit semiconducting behavior. Imagine, from insulating to semiconducting, all due to the magic of resonance. And guess what? This discovery has fueled the realm of plastic electronics. These cutting-edge technologies include lightweight and flexible organic solar cells, organic transistors, organic light-emitting diodes, and other devices that rely on carbon-based materials rather than traditional inorganic semiconductors such as silicon. Are you ready to explore further? Let's move on to the next topic and dive into the captivating world of these innovative carbon-based devices. Welcome back, Hello again, students. Our fascinating journey continues with a focus on nanomaterials, a truly unique category of solids. These solids have captivated scientists and engineers due to their extraordinary properties that emerge from their tiny crystal dimensions. When we talk about nanomaterials, we're referring to solids whose individual crystals have been shrunk to the range of 1 to 100 nanometers. Yes, that's incredibly small. But don't be fooled by their size. Nanomaterials exhibit remarkable changes in their properties. Even conventional materials we're familiar with can showcase entirely different behaviors at the nanoscale. Imagine the possibilities that arise when we manipulate materials at such a minuscule level. Stay curious as we journey further into the world of unconventional solids. Hello again, Welcome back, dear students. Today, we're diving into the mesmerizing realm of nanomaterials and nanotechnology. But before we plunge in, let's clarify what the term nano really means. Nano represents the scale of 10 to the power of -9. Now, when people mention nanotechnology, they're often talking about creating devices that exist on a minuscule scale, specifically within the range of 1 to 100 nanometers. You might be wondering, why is this size so special? Well, as it turns out, the properties of materials, like semiconductors and metals, undergo intriguing changes at this tiny scale. This brings us to the spotlight of today's discussion: nanomaterials. These are materials with dimensions within the 1 to 100 nanometer range, and they're sparking immense interest in research labs across the globe. And guess what? Chemistry is right at the heart of this exploration. Nanoparticles, which are a key player in nanomaterials, are remarkably larger than individual atoms, ranging from 10 to 1,000 times bigger. So, let's journey further into the world of nanotechnology and uncover the secrets of the nanoscale. Welcome back. Hello again, curious minds. Now that we're acquainted with nanomaterials, let's delve into their captivating properties. The nanoscale isn't just smaller, it's a realm of its own with distinct characteristics. Here's the magic: quantum effects and the significant surface area to volume ratio. Imagine, at this scale, materials can exhibit properties vastly different from their bulk counterparts. Enhanced reactivity and catalytic activity are among the standout features. How about optics and electronics? Nanomaterials have the power to absorb, emit, and manipulate light in extraordinary ways, thanks to their size. And let's not forget the importance of chemistry in understanding and tailoring these properties. Chemistry lets us engineer nanomaterials to have specific functionalities, opening doors to groundbreaking applications. So, buckle up, because we're about to uncover the fascinating world of nanomaterial properties. Hello again. Welcome, dear students. Today, we're delving into the captivating realm of semiconductors on the nanoscale. We're going to explore how the behavior of electrons changes as we move from small molecules to larger solids. You see, in small molecules, electrons have discrete molecular orbitals, while in larger macroscale solids, these electrons occupy delocalized bands. An interesting question arises. At what point does a molecule shift from having localized molecular orbitals to behaving as if it has delocalized bands? The answer, my curious learners, lies in the fascinating range of 1 to 10 nanometers, roughly equivalent to about 10 to 100 atoms across. Now, let's journey further to understand the specifics of this transition and the world of semiconductors. Welcome, dear. Greetings, young minds. Let's dive deeper into the scientific magic behind this transition in semiconductors. You're already familiar with how quantum mechanics describes electrons within atoms. Well, that same set of equations can also be extended to describe electrons and holes within semiconductors. By applying these equations, we can estimate the size at which materials shift from having discrete molecular orbitals to possessing delocalized bands. And where does this transformation really become significant? Right in the range of 1 to 10 nanometers. This range is incredibly vital in understanding the behavior of materials at the nanoscale. Now, let's proceed to unravel more of the mysteries hidden within this size-dependent transition. Greetings, young. Hello, inquisitive learners. Prepare to be amazed by a term you'll likely encounter frequently in the world of nanoscale semiconductors: Quantum dots. Quantum dots are semiconductor particles that fall within the size range of 1 to 10 nanometers. Remember that transition we discussed earlier, where materials shift from molecular orbitals to bands? Well, this is the realm where quantum dots reside. What makes them so intriguing? Their size-dependent behavior gives them remarkable properties, leading to a wide array of applications in fields like electronics, medicine, and even quantum computing. As we journey forward, you'll discover just how these tiny dots hold enormous potential. Hello again, knowledge seekers. Now that we've grasped the fundamentals, let's take a tour of the incredible applications that arise from this fascinating transition. Quantum dots hold immense potential in various fields. In the realm of electronics, they're utilized in cutting-edge displays, sensors that detect even the slightest changes, and high-performance transistors. But that's not all. Quantum dots are making waves in medicine, playing a pivotal role in imaging, targeted drug delivery, and advanced diagnostics. Oh, and let's not forget the captivating world of quantum computing, where quantum dots serve as the building blocks of qubits, the fundamental units of quantum information. As we conclude our journey, remember that even at the nanoscale, possibilities are boundless. Hello again, congratulations, explorers of knowledge. Let's take a moment to recap our journey through the captivating world of semiconductors on the nanoscale. We've learned about the intriguing transition from localized molecular orbitals to delocalized bands, and how this shift occurs within the vital range of 1 to 10 nanometers. Quantum dots, those remarkable nanoscale entities, are born from this transition, showcasing unique properties that find applications in electronics, medicine, and quantum computing. Keep in mind the influence of size on these properties and the power we hold to manipulate them. As you venture forth, remember that the world of nanotechnology holds endless opportunities for discovery and innovation. Now, go forth and continue your exploration of the unseen and the small. Congratulations! Welcome back, eager minds. Today, let's focus on the incredible contributions of chemists to the development of materials that power our world. Picture this. Chemists are like wizards, conjuring up new substances that didn't even exist before. They're the masterminds behind inventing novel materials that hold unique qualities. But that's not all. Chemists are also the architects of change. They have the power to process natural materials in ways that transform them into substances with specific properties. Imagine turning a mundane material into something with exceptional electrical, magnetic, optical, catalytic, or mechanical traits. These chemically engineered materials form the backbone of our technology-driven society. Now, let's dive into the nitty-gritty of solid materials and explore their structures and mesmerizing properties. Welcome back. Welcome, students, to an intriguing topic in the realm of semiconductor physics. Today, we're delving into the fascinating effects of reducing the size of a semiconductor crystal on its band gap. Now, what's a band gap, you might ask? Well, it's essentially an energy range in a material's electron structure, where no electronic states can exist. As we shrink semiconductor crystals to sizes ranging from 1 to 10 nanometers, something remarkable happens. The band gap changes significantly. This change becomes even visible to the naked eye. But before we explore the visual changes, let's understand the concept a bit better. Welcome, students. Alright, students. Let's delve deeper into the connection between band gap and crystal size. As we reduce the size of the semiconductor crystal, a striking phenomenon occurs. The band gap actually increases. This might sound counterintuitive, but it's a crucial concept. Now, how does this affect the material's appearance and behavior? Let's find out. Alright, student. Let's focus our attention on a specific semiconductor, cadmium phosphide. When this material is in its bulk form, it appears black to us. The reason behind this color is its relatively small band gap, which is about 0.5 electron volts, eV. This small band gap enables it to absorb all wavelengths of visible light, giving it that distinct black appearance. However, as we venture into the realm of smaller crystals, something mesmerizing occurs. Let's focus our Picture this, students. As we continue reducing the size of cadmium phosphide crystals, the band gap grows larger. This change has a remarkable impact on the material's appearance. The smaller crystals gradually shift from black to white. Why white? Well, with the band gap's expansion, these tiny crystals stop absorbing visible light altogether. As a result, they reflect all visible colors, creating the sensation of whiteness. Picture this. Good day, students. Today, we're venturing into the realm of quantum dots and exploring a fascinating method of their creation. Quantum dots are nanoscale semiconductor particles with unique properties that make them incredibly useful in various applications. Our focus today is on how these quantum dots are synthesized using chemical reactions in a solution. Imagine you're in a lab, aiming to create quantum dots like CDs. One way to achieve this is by mixing cadmium nitrate and sodium sulfide in water. Now, if you were to simply let the reaction proceed without any additional steps, you'd end up with large crystals of CDs. But here's where things get interesting. Good day. To better control the process and create quantum dots of uniform size and shape, we introduce a clever strategy. We add a negatively charged polymer, like polyphosphate, to the water before the CD synthesis. Think of this polymer as a plate of delicious spaghetti, and the CD2+ ions as tiny meatballs. These meatballs, CD2+ ions, associate with the polymer strands, creating a unique interaction. It's like our meatballs are getting entangled in the polymer spaghetti, creating a distinct environment for further reactions. To better control the process and create quantum dots of uniform size and shape, we introduce a clever strategy. We add a negatively charged polymer, like polyphosphate, to the water before the CD synthesis. Think of this polymer as a plate of delicious spaghetti, and the CD2+ ions as tiny meatballs. These meatballs, CD2+ ions, associate with the polymer strands, creating a unique interaction. It's like our meatballs are getting entangled in the polymer spaghetti, creating a distinct environment for further reactions. To better control the process and create quantum dots of uniform size and shape, we introduce a clever strategy. We add a negatively charged polymer, like polyphosphate, to the water before the CD synthesis. Think of this polymer as a plate of delicious spaghetti, and the CD2+ ions as tiny meatballs. These meatballs, CD2+ ions, associate with the polymer strands, creating a unique interaction. It's like our meatballs are getting entangled in the polymer spaghetti, creating a distinct environment for further reactions. To better control the Now, let's move forward with the CD's particle growth. When we introduce sulfide ions into the mix, CD's particles start growing. Here's the fascinating part. The polymer we introduced earlier doesn't just create an interesting visual analogy. It plays a crucial role in preventing these particles from forming large crystals. Imagine the polymer acting as a barrier, ensuring that the particles stay small and well dispersed. However, achieving this level of control requires a lot of careful adjustment of reaction conditions. It's like cooking the perfect dish. Every step matters in creating the desired outcome. Now, in the realm of photoluminescence, an electron residing in the valence band absorbs a photon. This absorption of energy causes the electron to be promoted to a higher energy level, the conduction band. Think of it as the electron getting an energy boost and moving to a new position. In the realm of But what goes up must come down. In the world of photoluminescence, the excited electron eventually falls back to the valence band, leaving behind a hole. This process of electron recombination results in the emission of a photon. And here's a fascinating detail. The energy of this emitted photon is precisely equal to the band gap energy of the semiconductor. This energy determines the color of the emitted light. Which means different materials can emit different colors. But what goes up must. Now, let's explore a remarkable phenomenon in semiconductor science: quantum dots. These are incredibly small semiconductor particles, and their unique property is that their band gap can be tuned by adjusting the crystal size. This tunability allows us to obtain a dazzling array of colors from just one material. Imagine the entire rainbow stemming from a single substance. An illustrative example of this phenomenon can be observed with cadmium selenide, as depicted in Figure 12.44. Now, as we conclude our exploration of photoluminescence, let's take a moment to appreciate its practical applications. This fascinating phenomenon isn't just confined to textbooks, it's at the heart of various technologies. Think of the vibrant displays on our screens, the energy-efficient LED lighting that illuminates our world, or even the sophisticated biological imaging techniques. By manipulating the band gap and harnessing the power of quantum dots, we're able to create materials that drive these advanced technologies forward. So, remember, the world of semiconductors and photoluminescence is not only intriguing, it's shaping the way we experience light and color in our daily lives. As we Welcome back, students. Today, we're delving into an exciting realm of technology that involves some truly remarkable structures called quantum dots. Quantum dots have been gaining significant attention due to their incredible properties and diverse range of applications. Imagine something incredibly bright and stable at the nanoscale. That's what quantum dots offer. These tiny structures are known for their unique characteristics that set them apart from other materials. But what makes them so special? Let's explore their incredible potential across various fields, from electronics to lasers and even medical imaging. Welcome back, students. Now, let's explore how quantum dots are making waves across different domains. In the realm of electronics, quantum dots are being harnessed to create vibrant and efficient displays. Their ability to emit specific colors makes them incredibly useful for high-quality screens that captivate our visual senses. Moving on to lasers, quantum dots are proving to be excellent laser emitters. Their unique properties allow for precise control over the emitted light, which is a boon for laser technology. And the excitement doesn't stop there. Quantum dots are poised to revolutionize medical imaging. Their ability to emit specific wavelengths of light is leveraged to create contrast agents, enhancing our ability to see inside living organisms. Even when coated with a biocompatible surface, these dots can be taken up by living cells, paving the way for innovative imaging techniques. Now, it's truly fascinating, isn't it? Quantum dots, even after being coated with a biocompatible surface, retain their unique properties. This coating allows them to be taken up by living cells, a capability that holds immense promise for various applications. Imagine being able to observe the intricate processes happening within living cells at a nanoscale level. Quantum dots enable us to do just that. By being absorbed into cells, they provide a window into the inner workings of life itself. This breakthrough opens up new avenues for intracellular imaging and advanced studies that were once beyond our reach. Quote, "It's truly fascinating." As we wrap up our exploration of quantum dots, remember that their potential goes beyond what we've discussed today. These tiny structures are pioneers in pushing the boundaries of science and technology. By harnessing their unique properties, scientists, engineers, and researchers from various fields are working together to drive innovation forward. The incredible brightness, stability, and cellular uptake capabilities of quantum dots are reshaping the way we approach electronics, lasers, medical imaging, and more. This journey highlights the power of interdisciplinary collaboration and the remarkable outcomes it can yield. Thank you for joining me in uncovering the world of quantum dots. As we wrap up our Welcome, students, to our exploration of a fascinating aspect of semiconductor physics, quantum confinement. In the world of semiconductors, we often associate properties with their size, and quantum confinement is a perfect example of this phenomenon. Imagine this. Semiconductors don't always need to be scaled down in all three dimensions to exhibit unique properties. Instead, they can be spread out in large, two-dimensional areas on a substrate, while maintaining an incredibly thin thickness, often just a few nanometers. This gives rise to what we call quantum wells. In these quantum wells, measurements taken along the nanoscale dimensions reveal intriguing quantum behaviors. But what about their length? It's interesting that even though these structures are confined in one dimension, along their length, they still retain properties similar to those of the bulk material. Now, let's dive deeper into the world of quantum wires and explore how their dimensions play a role in their properties. Welcome, students. Hello again, dear students. Today, we're venturing into the intricate world of quantum wires. As we've seen, quantum confinement is not limited to two-dimensional structures. It also extends to long, slender entities called quantum wires. These wires have an extraordinary characteristic: their diameter is on the nanoscale, often just a few nanometers, but their length can stretch significantly. Here's the remarkable part. When we examine these wires along their nanoscale dimension, we observe quantum behavior manifesting due to their confined nature. Yet, when we shift our focus to the length dimension, something intriguing happens. The properties exhibited in this long dimension resemble those of the bulk material. It's as if the wire's length allows it to maintain the essence of the larger semiconductor world. Now that we've explored the intricacies of quantum confinement in both quantum wells and wires, let's connect this knowledge to the broader context of semiconductors. Hello again, dear. Great job, everyone! Let's take a moment to recap what we've learned about quantum confinement in semiconductors. We've seen how even in two-dimensional areas, semiconductors can be tuned to exhibit remarkable properties when confined to just a few nanometers in thickness. The same holds true for quantum wires, where a minuscule diameter combined with a significant length brings about unique behavior along the nanoscale. It's important to note that in both cases, while we see quantum effects in the confined dimensions, the extended dimensions mirror the properties of the bulk material. Now, you might be wondering, why does this matter for the world of semiconductors? The implications are vast. These quantum-confined structures open doors to new possibilities in electronics, optics, and other technological applications. By harnessing these properties, we can create innovative devices with enhanced performance. As we conclude our journey through the world of quantum confinement, remember that the realm of nanoscale physics is full of surprises, waiting for curious minds like yours to explore. Keep up the excellent work, and stay curious. Great job, everyone! Hello again, students. Today, we're delving into the captivating realm of nanoscale effects on metals. Buckle up, because this is where things get truly intriguing. As we shrink down metals to sizes ranging from 1 to 100 nanometers, we enter a world of unique properties and unexpected phenomena. Now, let's talk electrons. You've probably heard that electrons are the tiny particles orbiting an atom's nucleus. Well, in metals, these electrons have a certain freedom to move around, creating what we call a sea of electrons. But when we enter the nanoscale, something fascinating happens. Imagine this sea of electrons encountering a shore, which is the surface of our tiny metal particle. The mean free path of these electrons, that's the distance they travel between collisions, at room temperature happens to be about 1 to 100 nanometers. When our metal particle's size matches or falls below this range, the behavior of these electrons changes, leading to some truly unusual effects. So, you see, even on the atomic scale, metals have surprises in store for us. Now, let's proceed to uncover more secrets of the nanoscale world. Hello again, Hello, dear students. Today, we're embarking on a journey into the intriguing realm of nanoparticles and their exceptional properties. You see, when we talk about materials at the nanoscale, things get quite fascinating. Metallic nanoparticles possess a range of unique characteristics that distinguish them from their bulk counterparts. For instance, let's take a closer look at gold particles. When these particles are less than 20 nanometers in diameter, they exhibit properties that are remarkably distinct from bulk gold. This difference in properties arises due to the quantum effects and increased surface-to-volume ratio at the nanoscale. So, imagine having a piece of gold that's smaller than you can even see. It behaves in ways that might surprise you. Alright, let's proceed to explore more about these captivating nanoparticles. Hello, dear Good day, young minds. As we delve deeper into the world of nanoparticles, let's unravel the role of quantum effects and surface area. When materials are at the nanoscale, quantum effects become prominent. This means that the behavior of particles becomes influenced by the rules of quantum mechanics, leading to unexpected properties. Moreover, due to their small size, nanoparticles have a much larger surface area compared to their volume. This heightened surface-to-volume ratio can drastically alter the material's reactivity, electrical conductivity, and even its color. Ever wondered why gold nanoparticles appear so vibrant? Quantum effects are at play, giving rise to colors that vary based on particle size. So, remember, even the tiniest specks can hold remarkable surprises. Good day, young minds. Welcome back, curious learners. Today, we're exploring another astounding aspect of nanoparticles, their catalytic activity. Prepare to be amazed by the potential these small wonders hold. Nanoparticles possess enhanced catalytic capabilities compared to their bulk counterparts. This makes them highly valuable in catalyzing chemical reactions. Even our friend gold joins the game. Gold nanoparticles, when employed as catalysts, exhibit remarkable efficiency in driving various reactions. This unique property finds applications in industries ranging from pharmaceuticals to environmental remediation. Imagine how these minuscule agents can play a pivotal role in creating cleaner and more efficient processes. So, keep in mind that size doesn't always matter, it's the impact that truly counts. Welcome back. Greetings, eager minds. Our exploration of nanoparticles takes us to the realm of medicine and biology. Believe it or not, nanoparticles have the ability to seamlessly interact with biological systems. This compatibility opens doors to exciting biomedical applications. Gold nanoparticles, for instance, have found their way into medical imaging and drug delivery. Imagine tiny particles guiding doctors to identify and treat diseases more effectively. But the marvels don't stop there. Nanoparticles can even be tailored to deliver drugs specifically to cancer cells, making treatments more precise and minimizing damage to healthy tissue. The future of medicine is indeed filled with incredible possibilities, all thanks to these extraordinary nanoparticles. Ready to dive further into this captivating world? Greetings, Good day, students. Today's lesson takes us into the realm of nanotechnology, where we'll explore some intriguing properties of nanoparticles. Our journey begins by investigating how size can dramatically influence the behavior of materials. Imagine this. Gold, a metal known for its unreactive nature, undergoes a surprising transformation when it comes to the nanoscale. When gold particles are tiny, ranging from 2 to 3 nanometers in diameter, they exhibit behaviors that differ from their bulk counterparts. For instance, these nanoparticles melt at significantly lower temperatures than larger chunks of gold. Even more astonishing, in this size range, gold loses its nobility and becomes chemically reactive. This phenomenon challenges our conventional understanding of materials and opens up exciting possibilities in various fields. Now, let's delve deeper into the world of nanoparticles and their fascinating size-dependent properties. Good day, student. Great to have you back, students. Our exploration of nanoparticles continues with a focus on the surprising reactivity of nanoscale gold. As we've discussed, when gold particles are in the nanometer range, they undergo a remarkable change. Normally unreactive bulk gold suddenly becomes chemically active. Why does this happen? Well, the key lies in the exposed surface atoms. At the nanoscale, a larger proportion of atoms are on the surface, and these atoms are incredibly active due to their increased exposure. This heightened reactivity leads to enhanced interactions with other substances, which can be harnessed for various purposes, such as catalysis and sensing. Isn't it fascinating how a material's size can completely alter its behavior? Great to have you back. Welcome back, everyone. Now that we understand the unique properties of reactive nanoparticles, let's explore some of the incredible applications that stem from this phenomenon. One of the most exciting areas is catalysis. Reactive nanoparticles can act as catalysts, facilitating chemical reactions that might otherwise be challenging or slow. Their increased surface area and reactivity make them ideal candidates for driving reactions efficiently. These nanoparticles also shine as sensors, detecting even the tiniest changes in their environment. In the medical realm, reactive nanoparticles are revolutionizing targeted drug delivery. By functionalizing these particles, we can guide them to specific areas of the body, maximizing treatment efficacy while minimizing side effects. As we've learned today, size truly matters in the world of nanoparticles. Welcome back, everyone. Hello again, students. As we wrap up our discussion on nanoparticles, let's zoom out and appreciate the broader implications of nanotechnology. By harnessing the power of nanoscale materials, we're diving into a realm where we can manipulate matter at the most fundamental level, the atomic and molecular scale. This opens up a world of possibilities across numerous industries. From electronics that are smaller, faster, and more efficient, to advancements in renewable energy and materials with unprecedented properties, nanotechnology is reshaping our future. Remember, the properties we've explored today are just the tip of the iceberg. As technology continues to evolve, so will our understanding and utilization of nanoparticles. Thank you for joining me on this exciting journey through the world of nanotechnology. Hello again, students. Today, we're delving into the fascinating realm of nanoscale properties, where elements like silver and gold reveal captivating characteristics. Interestingly, at the nanoscale, silver exhibits properties analogous to those of gold. This includes their mesmerizing colors. However, it's important to note that silver, despite its similarities, is more reactive than gold. Now, let's venture deeper into this captivating world. Welcome back, students. Our exploration now takes us to the exciting field of metal nanoparticles and their remarkable optical properties. Research laboratories worldwide are buzzing with curiosity and excitement about these properties. Why, you ask? Well, it's because these unusual optical characteristics of metal nanoparticles hold immense potential for practical applications. Specifically, these nanoparticles are garnering attention for two major fields: biomedical imaging and chemical detection. Just imagine the possibilities of using these tiny particles to enhance our ability to see inside the human body and detect chemicals with incredible precision. It's truly groundbreaking work happening on a global scale. Welcome back, Hello again, bright minds. Now, let's shift our focus to another remarkable application: chemical detection using metal nanoparticles. These tiny particles are like detectives at the molecular level, helping us identify and analyze various chemicals. The sensitivity and selectivity they offer in detecting different substances are unparalleled. This makes them incredibly valuable in fields like environmental monitoring and ensuring safety. Consider gold nanoparticles, for instance. They have the ability to detect pollutants in water sources, providing us with critical information for maintaining the health of our environment and population. Hello again. Welcome back, enthusiastic learners. As we near the end of our exploration, it's crucial to understand the global scale of interest in metal nanoparticles. Research laboratories all around the world are investing time and effort into unraveling the potential these nanoparticles hold. We're at the brink of revolutionary advancements that could reshape various industries. What's truly exciting is the collaborative nature of this endeavor. Experts from diverse disciplines are coming together to unlock new applications and possibilities. So, as you can see, the journey into the world of nanoscale wonders is one of boundless curiosity and endless opportunities. Welcome back. Hello, dear students. Today, we're delving into the world of carbon on the nanoscale. We've already learned about carbon's intriguing versatility in its bulk forms, such as diamond and graphite. But did you know that carbon can take on even more remarkable forms at the nanoscale? In the past 30 years, scientists have made groundbreaking discoveries. They've found that when carbon atoms arrange themselves in sp2 hybridized structures, amazing things happen. These structures not only include discrete molecules but also one-dimensional nanoscale tubes and two-dimensional nanoscale sheets. And the exciting part? Each of these forms exhibits unique and captivating properties. Let's explore further. Hello, dear. Greetings, bright minds. Our journey into the nanoscale world of carbon leads us to the captivating realm of one-dimensional nanoscale tubes. These tubes are formed when sp2 hybridized carbon structures arrange themselves in a particular way. What's truly astonishing is that these nanotubes possess exceptional properties. Imagine having tubes with remarkable mechanical strength and outstanding electrical conductivity. These characteristics open up a world of possibilities for applications in electronics, materials science, and beyond. So, keep your curiosity burning as we move on. Greetings. Hello, inquisitive minds. Now, let's explore the realm of two-dimensional nanoscale sheets, another astonishing creation of sp2 hybridized carbon. These sheets form when carbon atoms arrange themselves in a particular pattern. What's truly mind-boggling is the extraordinary set of properties these sheets possess. Picture this: remarkable flexibility, impressive transparency, and surprising strength, all packed into a structure that's just a few atoms thick. These qualities make these sheets incredibly valuable for applications in electronics, coatings, and various other fields. Let's continue our journey. Hello, welcome back, eager learners. Today, we're going to delve into the remarkable world of one-dimensional nanoscale tubes and two-dimensional nanoscale sheets made from sp2 hybridized carbon. As we've seen, these structures boast diverse and exceptional properties that could potentially revolutionize the world of materials science and technology. Just imagine the incredible advancements that could stem from this field. And remember, the journey is far from over. Scientists are continuously exploring and unraveling the mysteries of carbon on the nanoscale, unveiling new discoveries that could shape our future in unimaginable ways. Keep your curiosity alive as we conclude this part of our lesson. Welcome back. Great job, everyone! Now that we're familiar with the concept of unit cells, let's explore the arrangement of atoms within these units. Imagine the atoms as guests attending a grand ball within the unit cell. The positions of these atoms are meticulously defined, and this arrangement contributes to the crystal's unique structure. From simple arrangements to more intricate ones, the atoms within the unit cell play a crucial role in shaping the overall crystal lattice. As we delve further, you'll see how this atom arrangement influences the properties of different crystals. Great job, everyone! Welcome back, students. We've just taken a glimpse into the intriguing world of Buckminster fullerenes, or buckyballs. But did you know that the story doesn't end there? After the discovery of SEEB, scientists went on to unveil other molecules composed solely of carbon atoms. These carbon-based cousins of buckyballs are collectively known as fullerenes. Now, what exactly are fullerenes, you might wonder? Fullerenes refer to a broad category of carbon molecules that can have diverse structures and properties. They have sparked a lot of interest due to their unique arrangements and potential applications. Imagine it as a whole new class of carbon compounds that we're still uncovering and understanding. As we continue our exploration, keep in mind the incredible versatility and possibilities that these molecules offer. Welcome back, students. Hello again, dear students. Our journey today is not just about chemistry, it's also about the fascinating interplay between science and the world around us. We've already learned about buckyballs and their captivating soccer ball-like structure. But did you ever wonder about the inspiration behind such a unique arrangement? Well, let's introduce the brilliant mind behind the geodesic dome, R. Buckminster Fuller. He was not only an engineer but also a philosopher who looked to nature and geometry for innovative ideas. The geodesic dome, one of his most notable creations, draws from the inherent efficiency and strength found in natural structures. This dome's design, with its interconnected triangles, is somewhat echoed in the arrangement of carbon atoms within a buckyball. It's truly remarkable how the beauty of nature can influence human creativity and scientific exploration. Now, let's move forward and continue our fascinating journey through the world of carbon molecules. Hello again, dear. Good day, students. Today, we're delving into the captivating world of carbon molecules known as fullerenes. These molecules possess remarkable cage-like structures and fascinating properties. Our journey begins with the preparation of these intriguing molecules. We can actually create appreciable amounts of buckyballs by electrically evaporating graphite in the presence of helium gas. From this process, we obtain a mixture of carbon-rich gases, and about 14% of the resulting soot is composed of two primary fullerenes, C60 and C70. C60 is a spherical molecule, while C70 has a slightly more elongated structure. Interestingly, these carbon-rich gases also contain other fullerenes, such as C76 and C84, which have even more carbon atoms. Now, let's move on to explore the captivating world of fullerene solubility and separation. Good day, students. Welcome back, students. As we continue our exploration of fullerenes, we're uncovering their exceptional solubility and reactivity. Unlike substances like diamond and graphite, which are insoluble in various solvents, fullerenes exhibit an intriguing property: they dissolve in organic solvents. This distinctive solubility allows us to separate fullerenes from other components present in the soot. Furthermore, it opens up avenues for studying their reactions in solution. Now, let's dive deeper into the reactivity aspect. It's fascinating to note that smaller fullerenes, such as C20, display heightened reactivity compared to larger fullerenes. This reactivity leads to exciting possibilities for various applications. Welcome back, students. Null. Fantastic work, students. Let's wrap up our exploration of fullerenes with a look at their diversity and a final thought. In the year 2000, a breakthrough occurred with the discovery of the smallest fullerene, C20. This tiny, ball-shaped molecule introduced us to a world of incredible possibilities. We've discussed various fullerene structures with differing carbon atom counts, from the spherical C60 to elongated C70 and beyond. Fullerenes exemplify the marvels of molecular diversity and how different arrangements of carbon atoms can result in distinct properties and applications. As we conclude our journey, remember that the world of chemistry constantly surprises us with its intricacies and potential for innovation. Keep your curiosity alive and continue exploring the mysteries of the molecular realm. Thank you for joining me on this captivating adventure. Fantastic work! Welcome back, students. Now that you have a visual of carbon nanotubes, let's delve into how these remarkable structures are actually formed. The process is somewhat reminiscent of rolling up a sheet of graphite, like you would roll up a poster. Various methods are employed to create carbon nanotubes, each contributing to their unique properties. And remember how I mentioned capping the ends with half of a C60 molecule? That's what gives carbon nanotubes their distinctive structure. Can you imagine the complexity and precision involved in crafting these miniature wonders? Keep your curiosity ignited as we proceed to our next section. Welcome back, students. Great to have you all with me. Now that we understand how carbon nanotubes are formed, let's uncover the incredible properties that make them so captivating. Imagine a material that's incredibly strong and durable, even on the nanoscale. That's what carbon nanotubes bring to the table. Not only that, but these tiny tubes also possess impressive electrical conductivity and remarkable thermal properties. Such a combination of characteristics opens doors to a multitude of applications in fields ranging from electronics to materials science. Think about it. A material with such strength and conductivity at this scale could revolutionize various industries. As we wrap up this section, keep in mind the potential impact these nanotubes might have on our technological landscape. Great to have you all with. Hello again, young minds. Our journey through the realm of carbon nanotubes continues with a look at their incredible versatility. Imagine these minuscule structures revolutionizing electronics, taking nanotechnology to new heights. But that's not all. Carbon nanotubes also have a profound impact on materials science. Imagine reinforcing materials at the atomic level, enhancing their strength and durability. Moreover, the world of medicine has not remained untouched. These nanotubes have shown potential in biomedical applications, including innovative drug delivery systems. As you can see, the impact of carbon nanotubes reaches far and wide, from the devices we use to the materials we rely on and even to the frontiers of medical science. Let's move forward with our exploration. Hello again, young. Welcome back, inquisitive minds. Our journey through the world of carbon nanotubes nears its conclusion, but our exploration is far from over. Ongoing research continues to unravel new facets of these structures, introducing us to even more astonishing possibilities. Just imagine the environmental and energy applications that could emerge from harnessing the unique properties of carbon nanotubes. However, as with any scientific advancement, there are challenges to overcome. Large-scale production remains a hurdle, but dedicated minds are working tirelessly to surmount it. As we stand at the precipice of a new era in materials science and technology, keep your curiosity ignited and your passion for discovery aflame. Our final thoughts on this topic await. Welcome back. Hello, dear students. Today's lesson will take us into the intriguing world of carbon nanotubes. These are remarkable structures with exceptional properties that set them apart from other solid-state materials. One astonishing fact is that carbon nanotubes can exhibit both semiconducting and metallic properties without any need for doping. This unique feature has led laboratories worldwide to delve into the creation and testing of electronic devices based on carbon nanotubes. But that's not all. Carbon nanotubes have more surprises in store for us. Let's dive deeper. Hello, dear. Alright, everyone. Let's continue our exploration of carbon nanotubes. Besides their electronic potential, these nanotubes also possess impressive mechanical properties. Imagine this. Individual carbon nanotubes are believed to be stronger than steel, if steel were the size of a carbon nanotube. This astounding strength comes from the unique carbon-carbon bonded framework that these nanotubes possess. Unlike metal nanowires of similar dimensions, carbon nanotubes have a nearly flawless structure. This gives them unparalleled strength and resilience. Let's proceed to unravel more about these incredible structures. Alright, Bravo, dear students! You've journeyed through the fascinating world of carbon nanotubes, and I'm truly impressed by your engagement. Let's wrap up our discussion with a quick recap. Carbon nanotubes display extraordinary properties: semiconducting and metallic behavior without doping, exceptional mechanical strength, and the ability to enhance composite materials. These tiny structures hold the potential to spark transformative technologies across industries. Remember, our understanding of nanotubes is just scratching the surface. Researchers around the globe are continuously exploring and unraveling the mysteries of these incredible materials. As we conclude today's lesson, I encourage you to ponder the countless possibilities that nanotechnology brings to our ever-evolving world. Keep up the curiosity, and until our next lesson, stay curious and keep exploring. Bravo, dear. Hello, everyone. Today, we're diving into the world of carbon nanotubes, an extraordinary form of carbon allotrope. These nanotubes can be formed in two distinct structures, multi-wall and single-walled forms. Multi-wall carbon nanotubes consist of tubes within tubes, much like a set of Russian nesting dolls. On the other hand, single-walled carbon nanotubes are composed of individual, single tubes. Now, let's take a closer look at the dimensions of these fascinating structures. Hello, everyone. Alright, let's delve into the intriguing behavior of carbon nanotubes. Depending on the diameter of the graphite sheet from which they're formed and how it's rolled up, carbon nanotubes can exhibit two primary behaviors. They can function as semiconductors or metals. Imagine them as versatile actors, adapting to different roles based on their structure. When the graphite sheet is rolled in a specific way, carbon nanotubes can behave as semiconductors, allowing for controlled electrical conductivity. On the other hand, certain arrangements transform them into metals, resulting in efficient conduction of electricity. This dual behavior showcases the incredible potential of these nanotubes in various applications. Alright. Great job, students! As we wrap up our exploration of carbon nanotubes, let's discuss their vast array of applications, and the exciting possibilities they offer. Due to their exceptional strength and lightweight properties, carbon nanotubes find their way into various fields. They're at the heart of nanotechnology, playing a pivotal role in developing next-gen electronics and advanced materials. Their remarkable conductive abilities, whether as semiconductors or metals, open doors to innovations we're only beginning to uncover. keep in mind that ongoing research continues to unveil even more exciting prospects for these incredible nanotubes. With that, we conclude our journey into the world of carbon nanotubes and their fascinating attributes. Great job, students! Good day, students! Today, we're delving into the fascinating realm of carbon structures, specifically focusing on graphene, a two-dimensional wonder. Now, I want you to imagine a carbon structure that's incredibly thin, just a single layer of atoms arranged in a honeycomb pattern. This is graphene, the most recent low-dimensional form of carbon that researchers have successfully isolated and studied. Surprisingly, even though scientists had been theorizing about its properties for over 60 years, it wasn't until 2004 that a group of dedicated researchers at the University of Manchester in England managed to isolate and identify these individual sheets of carbon atoms. Let's dive deeper into the story of how they achieved this remarkable feat. Good day, students. Alright, my curious minds. Let's explore the ingenious technique that allowed researchers at the University of Manchester to uncover the secrets of graphene. Imagine having a block of graphite, the same material found in your pencils, which is made up of numerous layers of carbon atoms. The researchers' method involved a step-by-step peeling away of these layers, kind of like unraveling the layers of an onion. And guess what tool they used for this delicate process? Adhesive tape. Yes, you heard it right. They would stick a piece of tape onto the graphite, and when they pulled it away, a thin layer of graphite would come off with it. By repeating this process, they managed to isolate individual layers, and voila, they eventually obtained single-layer graphene. It's remarkable how such a simple yet creative approach led to this groundbreaking discovery. Alright, welcome back, curious minds. Now that we have a basic understanding of how graphene was isolated, let's dive into its incredible properties. Imagine a sheet of carbon atoms arranged in a honeycomb pattern, like a microscopic chicken wire. This arrangement gives graphene its extraordinary strength and electrical conductivity. It's so strong that even though it's just one atom thick, it's incredibly tough. Not only that, but graphene also boasts exceptional heat conduction abilities, making it a fantastic material for various applications. Think about electronics, materials science, and more. The potential uses of graphene are practically limitless. As we wrap up our exploration of graphene, remember that this material holds the promise of revolutionizing various industries and technologies. Welcome back. As we reach the end of our journey into the world of graphene, it's crucial to understand the impact of this discovery. The isolation and study of graphene have opened up new vistas in the realm of materials science. The ongoing research in this field holds the promise of unveiling even more applications that could revolutionize how we perceive technology and materials. This tale of scientific discovery reminds us all of the importance of thinking creatively and trying out unconventional methods. After all, it was adhesive tape that played a pivotal role in uncovering graphene's potential. So, dear students, I encourage each one of you to embrace your curiosity, explore the unknown, and who knows? You might just be the next groundbreaking scientist, peeling away the layers of innovation and uncovering marvels that shape the future. As we reach the Good day, students. Today, we're delving into the extraordinary world of graphene and its remarkable properties. Our journey begins with its exceptional strength and thermal conductivity, which set it apart from other materials. In fact, graphene boasts a record-breaking thermal conductivity, even surpassing carbon nanotubes. But that's not all. Graphene's electronic structure is intriguing. It's classified as a semimetal, similar to a semiconductor with an energy gap of exactly zero. This unique combination of characteristics has a fascinating effect on the behavior of electrons within graphene. Let's explore further. Good day, student. Now, students, let's dive deeper into the intriguing behavior of electrons in graphene. The fact that graphene is two-dimensional has a significant impact. This property, coupled with its semi-metal nature, allows electrons to travel remarkable distances without scattering. To put it in perspective, electrons in graphene can journey up to an astonishing 0.3 micrometers without being deflected by other electrons, atoms, or impurities. This long-range travel capability sets the stage for some truly exciting possibilities. Let's move on to our next point. Now, students. Next up, students. We're about to uncover one of graphene's most impressive feats, its exceptional electrical conductivity. Graphene has the remarkable ability to sustain electrical current densities that are 6 orders of magnitude higher than what copper, a common conductor, can handle. Imagine the potential implications of this. Graphene's incredible conductivity could revolutionize the field of electronics and beyond. But there's more to explore, so let's keep the momentum going. Next up, Now, students, get ready to be amazed by another unexpected property of graphene, its ability to absorb sunlight. Even though it's an astonishingly thin material, only 1 atom thick, graphene can absorb a surprising 2.3% of the sunlight that reaches it. This may not sound like a lot, but considering its minimal thickness, it's quite remarkable. Researchers are actively exploring how this property can be harnessed for various applications. And speaking of applications, let's move on to our final point. Now, students, as we wrap up our exploration of graphene, let's shift our focus to its real-world applications. Scientists are currently hard at work, exploring ways to integrate graphene into a wide range of technologies. These include electronics, sensors, batteries, and even solar cells. The unique properties we've discussed today open up new avenues for innovation across multiple fields. So, students, keep an eye out for exciting developments in technology driven by the incredible capabilities of graphene. With that, we conclude our journey into the world of graphene and its extraordinary properties. Thank you for joining me on this enlightening adventure. As we wrap